In this video, we'll be talking about some of the actual equipment that we use when we're doing our surveying. There's a wide variety of different equipment that can be used, and in a large part, it will vary on how accurate the surveying needs to be, and also what sort of scales are we doing our surveying over. For example, if we're trying to survey out all of Western Australia, we're not going to want to use a 1 meter ruler or something like that. That would be crazy. And likewise, if we're trying to survey a very small area, we want something that's going to be quite accurate, not something that's inaccurate and won't give us good data over that particular area. This graph shows some of the different sort of techniques that we can use in surveying, from things like tachymetry, where we're looking at movement over a surface, maybe like a trundle wheel or something like that, through to satellites and remote imaging that we can use over much wider areas, and then small measurements with hands or with rulers or with some vernier calipers for much smaller areas. Likewise, we can use things like photogrammetry when we've got many points, or things like GPS when we've got fewer points. So looking at surveying, often our problem is that we want to survey points, as in the distance to that point and the bearing of that point from maybe another point or from north or something from a known point, like maybe a survey control point. So here we're looking at a combination of both distance and a bearing or an angle, which we can refer to as a vector. And we can measure those angles both in the horizontal plane, so how far it is along the horizon, but also on the vertical plane where we're looking at depression or elevation from the point that we're dealing with. So defining our horizontal angles, if we've got 3 vector points, A, B, and P, we can define our angle either counterclockwise or clockwise from these. And if we've got a closed figure, we can define it as either the outer angles or the inner angles within our enclosed figure. Now, when we're defining our vertical positions, remember we're looking at what sort of elevation we have from our horizontal plane, or what sort of depression we have from our horizontal plane. Our elevation will be positive, our depression will be negative from our horizontal plane. We can also specify that as a zenith angle. In zenith, we're looking at perpendicular to that horizontal plane and then moving up or down from that horizontal plane that we're dealing with. And we can easily compute that value. Now, one thing that we can do with these vertical positions that we've surveyed is work out the height of the particular point. If we know PB, which is the slope distance, the distance from the point we're measuring at to some sort of control point off in this distance, and we know the elevation or depression from the point that we're at, we can very easily, using some basic trigonometry, work out the height above or below our horizontal plane that we're dealing with. Now, there's a number of different instruments that can be used. One of them is the Dumpy Level. And basically, this is an optical way of doing land surveying for height. Basically, we have a small telescope. That telescope's mounted on the tripod, and that tripod is adjusted to be level. Often they'll have a small spirit level in there. And then a person off in the distance will hold a ruler at various points, and you look through the telescope and look where the line lines up with the position on the ruler. Based on that, you can work out the relative height from where you are at your control point, wherever that happens to be, to the point where the person's holding the ruler, just optically by seeing it. Now, similar things can be done with laser levels as well, where a laser line is projected over a ruler that can be seen by other people as well. Another tool that's being used, and this isn't a new tool, is a theodolite. Now, theodolites have been around for over 250 years. And they basically allow us to measure the angle both in our vertical plane and our horizontal plane between 2 different points. Essentially, here we've got a telescope that's mounted on a series of protractors, and those protractors allow us to measure with very fine accuracy what the angle is between one particular point and another in those 2 dimensions. What we typically have is some sort of a mark point that we put our theodolite over, we level it off so that as we move our theodolite, it's moving planar to the ground that we're dealing with. And as we move it up, it's moving perpendicular to the ground that we're working over. One thing it doesn't give us, though, is our distance to objects. And so what we'd need to do is measure that somehow using maybe some rope or a tape measure or some sort of a laser rangefinder or something like that. Now, theodolites used to be used and used to be quite common, but these days we typically use a total station. And a total station does similar things to a theodolite, but with a whole lot of electronic smarts in it, like built-in GPSs. It also has a distance measuring system that allows us to measure using EDM, the distance between our total station and the thing that we were measuring, a control point or something like that. It also has built-in memory to allow us to store a number of points and do calculations between those different points. Some total stations also have capability for remote control, where we can stand with our control point and we can remote control the total station to have it track a particular control point, for example, and take measurements based on that. That means in the field, we don't need as many people working in the field to do these surveys. Now, I mentioned it does these range finding measurements based on EDM. EDM, we're using a light that's not visible to a human eye, and we're looking at the phase change of that light as it's reflected back from a special reflector disc, which is someone will be holding out in the field. So we're looking at how many whole wavelengths we have, and coupling that with the phase change, we can very accurately work out what our distance is from the particular point that we're trying to survey. This diagram shows a few different application ways that this can be used. For example, looking at a control point that someone's holding on something. And so here you've got the classic two-person total station setup, where one person's using the total station and one person's holding control points at various points within the environment. You've got a one-man robotic system where the total station is stationary and isn't manned, and a person's moving around with various control points, and they can control where those control points need to be stored and log in values with the total station. And finally, a tracking station where total station's tracking something on a machine as it moves around the environment, for example. Now, I've already alluded to GPS several times, and we'll talk about GPS later on in terms of how we use it for our surveying and the sort of improvements in accuracy we can get using GPS. We've also previously talked about photogrammetry, strapping cameras onto a plane or onto a drone or something like that and taking pictures from the sky, allowing us to have an aerial survey. Now, those aerial surveys can be done with satellites as well, which obviously decreases our resolution for the same quality of camera, but allows us to survey a much wider area at once. We can also create digital terrain models, or DTMs, with something like LiDAR, where we're looking at the distance when we're taking our survey, an aerial survey, either from satellites or from a plane or from a drone or something like that. This allows us to survey an area and look at it topologically of how it changes and what discontinuities we might have. These aerial surveys can be done quite quickly. It doesn't require access into areas that might be difficult or dangerous to access. Typically requires less people to perform our survey. And we don't have delays to traffic and people having to stand by the road with stop signs and things like that. So there's some real benefits if we can use something like LiDAR and do aerial surveys to use this. Now, it's not just LiDAR in the air. We can also use LiDAR on the ground with terrestrial surveys. And it's very similar. We've got a laser rangefinder that we're scanning over a region. And as we scan it over a region, we work out the distance from our location where we're at to all the different points we're scanning. That scanning allows us to build a 3D point cloud. And that point cloud we can use to model or survey the area that we're dealing with.